Today we're working on a Bally Cybernaut. This was like 1985 when Bally was just getting ready to switch over to 6803 series of games. This is technically a -35 game, but this one's a little different. It's got a problem which we'll talk about in a second, but let me open this up and show you the inside. This looks like a -35 MPU board. In fact, it's really not. It's a 6802. So what they mean by that is the processor, which is up here, is normally on -17 and -35 games. You know, all the Ballys from 1980 or 1978 to 1985 is a 6800 chip for the processor. But this one is actually a 6802. So what is the advantage of the 6802? Well, for one, it means that you can use a crystal for the clock circuit instead of depending on the 9602 chip in the 74S37 chip. So it requires slightly less, has it maybe support circuitry to run a 6802, so it's a more versatile chip. It does have some more instructions, but since the code that runs here and here will work in either a -35 or the 6802 board, they didn't take advantage of any of the extra instructions that were available in the 6802. It also uses a different RAM. You can see that this one's blank and it's supposed to be, but here it has a 2114 RAM. Anyways, it boots the same. We'll turn it on and you get the initial flicker and then the 7 LED flashes. And has the same solenoid driver board as you're used to seeing, same lamp driver board, an extended lamp driver board, and a Bally Cheap Squeak soundboard. Now the problem with this game is we have very few CPU controlled lights. In fact, almost none. That right there is it. So all the stuff down here is not working, so we got to figure out why. If you remember your general solid state architecture, there's two types of lamps. There's general illumination, which is like what we see underneath these slingshots, the lights that are generally always on. And then there's computer controlled lights, and those would be these flashing lights. Those are controlled by the MPU board, or hence called computer controlled lights. On the inside of this game, I did check out the lamp driver board. What I did is, if we go over to the shop over to here, you can see I've got a Bally test fixture here, and I can put my lamp driver board on the test fixture and basically run a lamp test like this, and then all these lights should be flashing. That would indicate that everything on this board is working, and that's what I've already done that to make sure that I don't have any problems with the lamp driver board itself, because you know these things, they do get damaged every now and then, so it's good to have something, and this is a beautiful way to test that on my little homemade test fixture. So with the playfield lifted, I can see that on this style of Bally games that they've gone to these lamp matrix boards opposed to using discrete sockets. I mean, they do have some discrete sockets, like down here, the ones that are actually working are discrete sockets. And the thing that you'll notice is that there's a bus wire. That is, that there is a wire, a bare wire going between all the sockets, and that is 6 volts. And then each wire here goes to the lamp driver board, and these go up to SCR, silicone controlled rectifiers. There's one for each of these lamps on the lamp driver board, and the CPU grounds those, and that completes the circuit and turns the light on or off, depending on, you know, whether they're syncing it or not. So the first thing I like to do is put my meter, which is set to DC volts, and then put my red lead on the bus, and I should get around 6 or 7 volts. And you can see here I'm getting 6 volts. And that's good. That means that these are working. If none of the CPU control lights were working, I would suspect a fuse down here for the CPU control lights, and that would be pretty benign and easy to fix. But you see here I have 7 volts. Now if I go up to the ones that aren't working, like here is a string right here, here is a CPU control light, and I put my red lead on the bus wire there. Look at what it's doing over there. on the meter. It's jumping all around, but it's not showing me really any voltage, any DC voltage. It's basically less than 1 volt. Now remember, I am not testing like this. This is going to be an AC voltage because this is general illumination. I am testing DC, and I'm just putting my wire on the DC bus, and that goes up to this lamp, which is a computer controlled lamp. And you can see I have literally nothing. So we've got a problem. Somehow we've got voltage down here, but we're not getting voltage to any of these lamp boards and any of the surrounding CPU control lights. Before we get too far into this problem, one thing we should talk about is one thing that Bally and Gottlieb did on System 1s and System 80s, and Bally did this on the Dash 17s, Dash 35s, and 6803s, is they don't have a lamp matrix. That is, if we go back to our test fixture, there is no lamp matrix like what Williams used. Williams used an 8x8 row and column lamp matrix. The intersection of any two would give you a particular lamp being on. Bally did it different. Instead, they just had a power bus, which would be down the center. If you look here on my little LED thing, all these yellow wires are my 6-volt DC. And then they had a separate silicone controlled rectifier for each lamp. And there's 60 of these things on here. And you can see there's 2 types. There's these small ones, 2N5060s, which control 1 light, and these larger T106s, which can control 2 lights. So they had 60 of them, so if you wanted to turn on, say, this light right here that I'm pointing to, you would activate this SCR. You would either trigger it on or off. The advantage to not using a lamp matrix is there's no maintenance. Once you turn a lamp on, it's on. Once you turn it off, it's off. You forget about it in the code. I'm talking about in the code that's running inside the EEPROMs. With a lamp matrix, the voltage is actually like 18 volts, and you have to duty cycle it, and you have to strobe the lights. It's constant maintenance that the code has to update. And the problem with that is that means that the processor, which is this guy here, is only so fast and can only do so much. So if you have a lamp matrix, there's overhead, a lot more overhead than using this SCR and separate individual lamps controlled by each SCR. There's way less processing involved. So that allowed Bally to do a lot of things in their code that Williams could not do. And hence, Bally games are a lot more robust, in fact, in their gameplay and architecture, and could do a lot more things than, say, Williams could. You never saw, like if you look down our row of games here, there's no infinity lighting on any of the Williams games. There's no fancy really anything on Williams games. They're really pretty plain. Where on these series of games, you know, they could do all kinds of crazy stuff because they had the processor, you know, capability to do that. What we know is that we have 6 volts here, but we don't on any of these boards or on these controlled CPU lights. So why is that? It's because the power is daisy chained. So the 6 volts comes to the playfield. Usually it's going to come at the bottom of the playfield first because that's where the wiring comes in. That's going to be stop number 1, bus stop 1 as we'll call it. Get it? Bus stop 1. So it's this blue wire right here, and then you can see that it then daisy chains up and comes over to these boards. And again, we've got these little blue wires. And if you look at these boards, you can see this area on the trace, this big fat trace, that's supposed to be the 6 volts. And you can look here, there's 2 pins here and 2 pins there. If I take this connector off, you can see our magic blue wires, 2 here and 2 here. But the problem with this is that these wires aren't really connected unless they're connected to the board. So what happens is that they're connected at the solder point right there. So if that connector pins are bad, guess what? Everything downstream isn't going to work. So let's look at this connector here. This is actually bus stop 2 in the whole bus of power. And look at this right here. Can you see it? Look at those pins. They're burnt. They're smoked. Okay, this is the first point, and look, the connector housing is actually melted. Look at that. It's really melted. And if we look at the pin, I don't know, it's hard to see, but the pin's black right there. So this is our problem, is that these two wires are not connected. But look, what I've done is I've stripped back the wires just a little bit here, and if I touch these two together, which is hard while I hold the camera, let's see if I can do it. Look, all of a sudden, there's the rest of our CPU control lights. See how they're all flashing now? And now I will disconnect that. I will remove my, my pressure on these 2 points, and everything goes off. So how are we going to fix this? Well, obviously we're going to fix these connector pins. That's a no-brainer. We're going to do that for sure. But the other thing that we need to do is that we can actually tie these wires together outside of the connector pins so that we're not using this turnaround on the board to bring the 6 volts from wire to wire in the daisy chain. That is, the daisy chain will be hardwired up here before it gets to there. So that's going to be our best solution, and we can get all the lights working that way easier and not have to worry about if a pin burns for whatever reason. It's not going to influence everything downstream. So here's my wires tied together. If I wanted to get even more slick, I could tie this one to this one, put a little jumper between them. That would really probably be not a bad idea. And then I'll put heat shrink tubing over here, or you could use electrical tape, but heat shrink tubers cleaner and make this look a little better. So now I have the game in lamp test, and you can see I have nearly every CPU control bulb working. There's a few that aren't. I have like this one and this one I'll have to trace down. This one too, those 3. But one thing I wanted to do is I wanted to add some LEDs to this area up here, because it's just too dim and too hard to see. It was so far from the player, and the tube is kind of in the way. So I wanted to brighten them up. I don't know if you can tell, but these yellow ones I have LEDs installed, and then the red ones are incandescent and the clear ones are incandescent. You can probably see them flicker. This is a problem with LEDs on this system. We've talked about this before, but not in reference to these circuit boards. So what I'm going to do is I'm going to take this board out, and I'm going to put limiting resistors in, and show you how that takes this flickering away in the yellow. I'll also do the other ones in LEDs, but I just wanted them right next to each other for demonstration purposes, because I do want to make it a little brighter, at least some of them. I just think it's a better look on this particular game, not on every position or every game. I don't know if you could see it, but here's a kind of a better demonstration, or a different demonstration of the flickering I'm getting out of these lights. How they're not, these LEDs are not staying on. They flicker, and it's really bad. The camera kind of makes it look less of a problem, but it really is a huge problem when you see it in real life. So here's the lamp board that's been modified. Basically, I have to put 470 ohm resistors across the main power grid, which is this line all the way around and down the middle. That's the 6 volts, that's the power bus. And to each of the lights. So there's 1, 2, 3, 1, 2, 3, 9 lights. So there's going to be 9 resistors. And you can see I kind of got creative about where you place them. I just kind of wanted to make the shortest run I could. But now I think we're ready to put it back in the game and see how it does with the flickering, but this should pretty much eliminate the flickering. So here is the board. We've got the resistors installed, and you can see that the flickering is gone with the LEDs, so I can reinstall this. So let's try a game.